Hi. Are you able to hear me? Okay. Are you able to hear me? We're kind of in the backstage of Zoom.
I can hear you, Dr. Chacon.
Okay, great. I don't plan to have let me see, choose virtual background. Just make sure it works. Okay. All right, Emily, we can hear you. Kristen, how are you feeling? Okay, perfect. Nivi's here. Waiting for Blake from our team. Kristen, do you have the websites ready to go?
Yes, so I just have, let's see, the Facebook page, the YouTube, and then Dr. Malamad's blog, and then I guess the main page I should have up too.
Yeah, we just got approval to add a TikTok. So I don't know the logistics behind that, but if they just search EP Heat, they can find our TikTok, and we started add videos there too.
Okay, fantastic. I'm just trying to figure out how to change the virtual background real quick.
Okay, so on your video, just go to that up arrow, and then you should be able to choose a background. Yep, there you go. That looks great. Yep, Nivi, you're good. Let's see. Okay, Cole, look good. Are you able to hear us, Cole? Okay, perfect. Yep. All right, I'm excited. So we had about 30 people register. I haven't broadcasted it yet, but once I do, then let me stop.
Welcome, everyone. My name is Kristen Helmsdorfer, and I'm a first-year medical student at Texas Tech, El Paso. I had the honor of working with Dr. Esther Malamed at Dell Medical School in UT Austin. She is a board-certified neurologist and currently conducting NIH-funded COVID-19 research. Before moving to El Paso, where I met Dr. Jessica Chacon, who is a PhD scientist, immunologist, and helped to establish the El Paso HEAT, or EP HEAT, which stands for El Paso Education and Awareness Team, which has delivered about to 2,000 El Pasoans virtual COVID-19 educational health fairs. Both faculty have been absolutely instrumental in their mentorship, research, and education of COVID-19. And we are very excited to host our first ever joint panel between these two institutions today. In the next hour and a half, you will hear 6 10-minute presentations from undergraduate, graduate, and medical students, followed by a 30-minute question and answer session. I will be your moderator. Again, my name is Kristen. And if you have any questions, feel free to type them in the chat and we will answer them as best as we can. All right, with that, I'll go ahead and introduce our first panelist from Texas Tech, El Paso. He will give an overview of COVID-19. His name is Blake Mireles. He is an El Paso native and graduate of UTEP, or University of Texas, El Paso. He is currently attending the Graduate School of Biomedical Sciences at Texas Tech, El Paso.
All right, everybody. So I'm going to go ahead and share my screen. Can everybody can see it just fine?
Yes.
My name is Blake Mireles, as Christian said, and I am an El Paso native, and I'm a part of the Graduate School of Biomedical Sciences at Texas Tech University Health Sciences Center, El Paso. So I'm going to be giving a brief presentation on the overview of COVID-19 And that way we can provide you with a strong foundation in order to follow the rest of the presentations. So first, just a brief disclaimer, none of our presentations or demonstrations endorse or promote any proprietary products. And the presentation doesn't constitute any medical advice, and the individuals participating should contact their personal physician regarding any medical advice or any other questions on COVID-19. So we will go into why is COVID-19 called COVID-19? So we've heard a few different names, SARS-CoV-2, COVID-19, coronavirus. So coronaviruses are actually a large family of viruses that cause upper respiratory tract illnesses, such as the common cold. Now, SARS-CoV-2 is actually a strain of the coronavirus that causes COVID-19. And as you can see in this brief breakdown, so COVID comes from coronavirus disease. And since we first discovered it in 2019, that's where we get the 19 from. The transmission mainly comes through coughing, sneezing, especially droplets. I know we've heard that word quite a bit. This does spread person to person through the respiratory droplets. That's why it is very, very important to wear a mask. As we can see here, the peak exhalation speeds can reach up to 100 feet per second just for a sneeze. So it is very, very important to constantly have your mask, especially even if you're not coughing or sneezing all the time. It is always going to be important to protect you from somebody else around you that may be coughing or sneezing. The transmission of the virus, there's no current evidence that COVID-19 can be transmitted through food, but there is a possibility that may be on the surfaces, which I'll go over a little bit later. At this time, there's also no evidence that animals play a significant role in spreading the virus, but they can get the virus themselves. It should be noted that some pets, cats, dogs, have been reported to have been infected with the virus in several countries, including the United States. So most of the pets did become sick after contact with people with COVID-19. So while the data isn't exactly a wide-ranging amount, it might be best to social distance from your pet if you are feeling severe symptoms. And as of now, mosquitoes are not known to spread COVID-19. Now, I just updated this today so that way we can see the most current. As you can see, we do have a few population hotspots, and as of today, there have been 11,455,346 total tests with 1.3 million confirmed cases. The biggest hotspots that we see are Harris County, Dallas County, Tarrant County, which is around Fort Worth and Arlington, and El Paso County. So as we can see here, we definitely have the hotspots around the larger areas of the state. So definitely if you live in one of those areas, be sure to wear your mask and protect yourself. The deaths around Texas also continue to climb. As of today, we do have 21,186 total confirmed deaths. And all of these do come from the Johns Hopkins University website, should you want to take a look for yourself. But statewide, we are crossing some pretty high thresholds as of now. Now, I want to take a little brief moment to go over flu versus COVID mortality, because unfortunately, there's been a lot of very close comparisons between the two, and people are equating one means that you might have the other, or back and forth. And unfortunately, we can see from this graph that COVID mortality is quite a bit higher. There were 242,000 COVID-19 deaths reported in the US during the week ending April 21st, 2020. There were 14,000 COVID-19 deaths reported in the US during the week prior to that. Now, there were 351 flu deaths during the peak week, which was week 11 of 2016 of the flu season, which was in 2015 and 2016. So as you can see, there's a pretty big difference between the two. Now, I'm gonna note that this particular graph is El Paso specific. But as we can see, community transmission, such as going to the grocery store or going to the post office or things in that realm, is the largest source of infection exposure. Close contact, such as going to a relative's house or things like that, is the second largest, and traveling being the third largest. Close contact has gone up within the past week, and community transmission has gone slightly down. As we can see, the big difference in that are shutdowns of certain activities or certain social areas. Now, I want to take a brief minute to go over this pyramid so that way you can better understand the times where you should seek healthcare and be diagnosed. So in this case, once you're fatal, patients usually try and seek healthcare and can be diagnosed and isolated, and their contacts can be traced, which is obviously a benefit for not just yourself, but those around you. The caveat is that coronaviruses can have a propensity for for nosocomial spread. Now, mild or asymptomatic are usually sometimes the most dangerous because those are the ones that can be around others without knowing that they have the virus and unfortunately transmit it to others. And that can be very, very dangerous, especially around children who may not always know whether or not they have the virus. Some actions, and maybe something that you've heard over the past few weeks, is flattening the curve. Some of the graphs I showed you earlier, as we can see, it kind of goes in a peak wave. And right now what we're trying to do is flatten that curve so that way we can go ahead and move forward with our lives. This picture shows the incidence of COVID cases over time in any particular region. As we can see, the differences between the red peak, the blue peak, and the green peak on the bottom. Now, strong actions will have the best effect on flattening this curve. I'm gonna go ahead and take a minute just so you can go ahead and see the droplets do have a very large effect on the transmission of the virus. Now, COVID-19 is thought to spread from person to person via respiratory droplets. Current recommendation is to stay at least 6 feet apart. So we can see in the image that when an infected person with COVID-19 coughs or sneezes, microscopic droplets containing the virus are released into the air, and these virus-containing droplets can land just about anywhere. So it's best to go ahead and sanitize anytime you're around something, touching something, or whether you're around household objects and things even such as grocery carts or plastic bags, which we're gonna go into right here, which is how long can the coronavirus live on surfaces. So right here, we see that of the top ones, paper money, glass, plastic, and even stainless steel, the virus can last on those surfaces for a few days. These are the surfaces that pose the most risk, including shopping cart handles and shopping bags. So remember, if the cashier at your grocery store asks you paper or plastic, you say copper right away. Preventative measures for kids and adults. Now, this is probably the best way to do it, is we want to go ahead and stay 3 footsteps apart. You want to always make sure to have your masks on that will cover both your mouth and your nose. And we want to go ahead and make sure that we keep hand sanitizer close by at all times, so that way we can go ahead and limit the spread, even if you're not necessarily feeling symptoms. Here we go through a few symptoms of coronavirus: cough, shortness of breath, difficulty breathing, muscle or body aches, vomiting or diarrhea, and new loss of taste or smell. And those can be hallmarks of the coronavirus versus the flu or another upper respiratory illness. Some of the complications of COVID-19 can include blood clots, brain damage, and a potential for long-lasting lung damage. And as we can see in the most recent weeks, there's been quite a few athletes that have come down with coronavirus, and they do report having lasting lung difficulty when they're breathing or when they return to practice. Some of the risk factors associated with COVID-19 are below, and I will say that those over the age of 65 do fall into the category of being the most at risk, with diabetes actually having the strongest correlation to being an underlying factor. And lastly, just a few going over treatment. I'm actually going to leave it to Cole to go over this later in the presentation, but currently the treatment is just supportive, means it's taking aim at relieving the symptoms. So some of these are pain relievers like acetaminophen, cough syrup, rest, and fluid intake, almost like if you did have the flu. Acetaminophen is definitely preferred over ibuprofen, and remdesivir has been shown to reduce times in the ICU, meaning less ventilator time for the patient. So go ahead and stay tuned for Cole's presentation, when he will go over the more treatment. And finally, I want to say thank you, and here's our social media links should you want to go ahead and check up on those. All right, thank you very much.
Thank you so much, Blake. Next, we have Sam Bazzi. Sam is a PhD student in the Mulva lab. He received his Bachelor's of Science in Biochemistry and Cell Biology from the University of California at San Diego, and then worked for 2 years studying Alzheimer's disease. In the lab, he is currently assisting with the NIH COVID-19 funded research.
Hello, thank you, Kristen, for the introduction. So today I'll be talking to you about neurological disorders in COVID-19. So I first wanted to highlight an amusing finding from a data scientist on Twitter who analyzed Amazon reviews of scented candles over the past few years. And as you can see, the reviews began trending downward since the start of the pandemic, which of course coincides with the now well-known symptom of COVID-19, anosmia, which is the lack of smell. Besides anosmia and the lack of taste, ageusia, there have been many other neurological disorders that have been associated with COVID-19. Some that affect the peripheral nervous system include Guillain-Barré syndrome, dysautonomia, which is dysfunction of the autonomic nervous system, and skeletal muscle injury. Further, there have been more than a few cases of neurological disorders affecting the central nervous system, including stroke, encephalopathy, including acute necrotizing encephalopathy, encephalitis, meningitis, acute disseminated encephalomyelitis, also known as ADAM, which involves inflammatory damage to the myelin, and other forms of myelitis. And the prevalence of these neurological comorbidities with COVID-19 varies depending on the studies, but the prevalence among hospitalized patients seems to be between 36 and 62%, depending on who you ask. So it is relatively common. This then begs the question of how does COVID-19 affect the central nervous system? The brain normally does a pretty good job at keeping viruses and immune cells out, so what's going on? And there are two main hypotheses floating around to explain this. The first is direct viral entry of the virus via the ACE2 receptor. ACE2 is expressed on all sorts of cells that comprise the CNS, including neurons, oligodendrocytes, astrocytes, endothelial cells, and others. The issue is that in many of the case studies that I have looked at, there does not seem to be any presence of live virus within the cerebrospinal fluid of patients with encephalitis or other severe neurological events during COVID. And this might have to do with the difficulty in detecting small amounts of the virus, but regardless, we're still not 100% sure that this hypothesis is correct. The other main hypothesis, which is kind of a big umbrella, is indirect mechanisms. So things like massive systemic inflammation has been reported during COVID-19, including the cytokine storm. We've also seen permeabilization of the blood-brain barrier reported in severe patients, which would compromise the barrier and allow infected peripheral immune cells into the CNS compartment. It is also possible that the virus is carried through blood flow into the brain. Another interesting hypothesis is the generation of autoantibodies, which I will talk about later. It is important to note, however, that both hypotheses are still being evaluated and that neither one is working totally independently of the other, because there are contradictory findings across different types of studies that make it difficult to generalize at this point of our understanding. So now I'm going to go over some of the studies that highlight what we do know about how this virus affects the nervous system and the cells that comprise it. This first study I'll talk about utilized an in vitro model of the brain called brain spheres, which are made up of neurons, astrocytes, and oligodendrocytes. The authors cultured these brain spheres with live SARS-CoV-2 virus for 6 hours before thoroughly washing them multiple times to remove the initial viral inoculum. They then analyzed the viral genome copies of the virus at 6 hours and 72 hours post-infection. And they found that not only is the virus able to infiltrate the neurons, but it also is able to replicate within them. And you can tell that because the number of viral copies increased over the course of the experiment. There's also an increase in the viral genome copies of the supernatant as well, which implies that the virus is shedding from these cells as well. The images on the left show staining for the membrane and the spike proteins of the virus at 72 hours post-infection. So we know from the study that the virus can enter neurons and replicate within them in vitro, but we also want to know if this holds true in vivo or in humans. Hot off the press is a study published last week in Nature Neuroscience that analyzed postmortem tissue of individuals with COVID-19. And they utilized a lot of techniques, including immunohistochemistry, in situ hybridization, and electron microscopy to show that the virus does indeed infiltrate the olfactory epithelium and can then go on to infect sensory neurons and perhaps even other neurons downstream via axonal transport. I included one of their figures here, which shows co-localization of the spike protein of the virus, in addition to 3 different markers for cells of neuronal origin. Another aspect about viral entry that quite surprised me was the role that other receptors might play. At this point, it's quite clear that the 2 receptors receiving the most attention are ACE2 and TMPRSS2. However, another receptor called neuropilin-1 has been implicated in viral entry as well. And although it alone is not sufficient to allow viral entry, this paper published in Science showed that its presence alongside the 2 canonical receptors greatly enhances viral entry. Further, they found that NRP1 is highly enriched in cells from the bronchoalveolar lavage fluid of COVID-19 patients via single-cell seq, and that post-mortem tissues shows co-localization of NRP1 and the spike protein, which you can see here. The NRP1 is in purple. This really puts into perspective that there may be much more to the story of viral entry rather than just ACE2. The last study I'll talk about for now is in support of the other indirect hypothesis. This is a case of acute necrotizing encephalopathy associated with COVID-19. Now, this case study stood out to me because the authors found an unknown IgG antibody from the patient that bound to specific neurons when tested on brain slices from monkeys and rats. It bound to cerebellar slices in monkeys and to the hippocampus in rat slices. Other studies have found anti-SARS-CoV-2 antibodies, but not live virus, in the cerebrospinal fluid of COVID-19 patients with neurological symptoms, which points to other mechanisms such as blood-brain barrier dysfunction. I think this finding with the antibodies is really fascinating because there are a number of hypotheses of how viruses may mediate autoimmunity. And in the case of this virus, examples of how this virus may mediate autoimmunity. In general, viruses can generate autoimmunity in many ways, such as molecular mimicry, which is when a virus component shares structural similarity to a self-antigen. There's also epitope spreading, which is a feature of the immune system that allows it to be flexible in responding to a wide range of antigens. But we also know plays a part in mediating autoimmunity in some of our animal models of multiple sclerosis. There is also the potential for the bystander effect, which is the activation of existing T cells through cytokines rather than the T cell receptor activation. With the current virus, we've seen examples of autoimmune disorders affecting the nervous system, including Guillain-Barré syndrome, which affects the muscles and nerves in your legs and in your arms. There's also acute disseminated encephalomyelitis and Kawasaki-like disease. So there's still a lot of ground to uncover in this area, and some of the work we're currently doing here at UT Austin and Dell Medical is trying to answer some of these questions. I'll end this presentation by briefly touching on some of the post-COVID brain effects. There's a study that tracked long-haul COVID symptoms and found that among 60 COVID patients, 68% of them had neurological symptoms and during the acute stage of their disease. And at follow-up, 55% of them had long-lasting neurological symptoms. So the big takeaway point is that this virus can really affect your brain in pretty severe ways, and it's very important for us as scientists and the clinicians among us to be aware of them. Thank you for listening.
Thank you so much, Sam, for that presentation. Next, we have Manohar. She's a second-year medical student at Texas Tech El Paso. She has volunteered with EP Heat's virtual platform as part of the testing team to provide El Paso communities with up-to-date information on SARS-CoV-2 testing. She also leads a research team with the Community Action and Engaged Service Collaboration, studying the needs and assets of communities in the El Paso region with regard to the COVID-19 pandemic.
Okay, hopefully you can hear me now. Hi everyone, thanks for joining us today. My name is Nivi. I'm a second-year medical student at Paul Foster School of Medicine. I'm here representing the testing team and will be presenting on SARS-CoV-2 or COVID-19 testing. Okay, so a brief overview of our presentation. We'll be talking about just the current state of infectivity, where you can get tested, the different types of testing. We'll briefly talk about contact tracing, what to do if you test positive, when you should get tested, and we will, I guess, save questions for the question session at the end of everyone's presentations. So a brief look at the infectivity of SARS-CoV-2 in our population. So Blake briefly mentioned this, but we have had over 1.3 million reported cases of COVID-19 in Texas and around 23,000 deaths. Looking at the general trend, we're experiencing a new surge in cases with significantly increased hospitalization rates. So this just emphasizes that this virus is still very much present in our community and we should be taking the necessary safety precautions. And then for your reference, I've included a few links about where you can get tested. So here are two sites. The first is the Texas Department of Health and Human Services website. And then I also have Austin's website as well as El Paso's. And each of these websites provide further details such as the location, the testing location, hours of operation, if the testing is free, when you can expect to get test results back, and if you need to make an appointment and how. All right, so let's talk about the different types of testing. So there are three types of testing. There's diagnostic testing, which includes molecular and antigen testing. There's antibody testing, and then there's alternative diagnostic testing, which includes some new players on the scene. So let's take a look at each of these modalities. So first we'll talk about diagnostic testing, and in particular RT-PCR. So what is RT-PCR? So this is the most common type of testing being used right now in clinics and, for example, drive-through testing. It's a nucleic acid amplification test, meaning that it detects the virus's genetic material. And this is used to diagnose if you have an active coronavirus infection. So how does it work? A nasopharyngeal swab is collected and then transported to the lab. In the lab, this viral genetic material on the swab is extracted using a technique called PCR. Copies of the DNA are made. If viral genetic material was present, many copies of DNA are made, and this is measured as a positive test result. So why is this type of testing important? Again, this is going to tell you if you are currently infected and need to take precautions to self-isolate. One caveat I will mention is that some testing centers may take days to get back to people with results. So the best practice is to self-isolate if you suspect you may have COVID-19. All right, and then next we'll talk about antibody testing. So what is antibody testing? This type of test is less commonly done. It detects antibodies made by your immune system in response to a COVID-19 infection, and it's going to tell you if you were previously infected with SARS-CoV-2. So how does it work? A blood sample is collected, and in the lab, an ELISA test is performed, which detects and measures antibodies in the blood. And why is this type of testing important? So this test will not tell you if you have an active infection, but it will tell you if you were previously infected and produced antibodies in response to the infection. One thing to mention that it's not clear if having antibodies results in immunity to future infections, and there's a possibility, and we're not sure really how long the antibodies remain in blood and if there's a possibility to get reinfected. And then finally, let's look at a few of the alternative diagnostic testing modalities that have emerged. So a couple that I want to focus on is the rapid point of care test and saliva testing. So the rapid test, this test can be done on location. It works really similarly to molecular and antigen tests, and you can get the results in minutes. Saliva testing is quite similar, but the saliva will still need to be sent to a lab for analysis and might take days to get results, but it is a shorter amount of time than maybe antigen or molecular testing. So right now, both of these types of tests are not as accurate as traditional diagnostic methods, but it will improve the efficiency for systems and allow for more timely and widespread testing. Okay, next let's discuss what happens if someone you know tests positive or if you yourself test positive for COVID-19. So contact tracing is done by departments of public health to identify individuals who have COVID-19 and notify others who have come in close contact with them. It's an entirely anonymous process where people who have been exposed to COVID-19 are referred to testing. And the goal here is to have people self-isolate and stop the spread of disease. So what does self-isolation entail? So self-isolation should be done if you think you have been exposed to COVID-19. So for 14 days is what is recommended. You self-isolate, continue practicing social distancing and monitor for symptoms. There has been a new update and an option that the CDC has given to reduce quarantine time in case people need to return to work. So based on local availability of viral testing, if people without if you have, for people without, I apologize. For people without symptoms, quarantine can end on day 10 without testing or on day 7 without after receiving a negative result. And the health departments can provide support, information, and resources in case you have to go into self-isolation. Okay, and then we'll move on. So when should I get tested? So not everyone needs to get a COVID-19 test. So some reasons to get a test include having COVID-19 symptoms, having close contact with someone who's tested positive. So this is defined as being within 6 feet of a person with COVID-19 for at least 15 minutes. If you're in a high, and if you're in an area with a high caseload and have attended a gathering of greater than 10 people, this is also an indication to seek testing. And another relevant indication is if you're a healthcare worker or have been working in a nursing home. So to wrap this up on an important note, it is important to realize that you can be infected and spread the virus, but feel well and have no symptoms. And this really emphasizes the need for keeping up with safety measures like mask wearing and social distancing to really protect yourself and others. And this is a fun little graphic to show that, you know, COVID-19, the incubation time is up to 14 days. So the median is found to be 4 to 5 days from exposure for developing symptoms, but like this graphic shows, you know, you can be exposed to COVID-19, you can test negative on day 5, you can enjoy, you know, a holiday gathering, and then on day 10, it's possible that, you know, you were contagious and spread COVID-19. So just a word of caution as we enter the holiday season. Thank you.
Thank you so much for that presentation. Next, we have vaccine development by Parker Davis. Parker is an undergraduate student in the Mulva lab, pursuing a degree in microbiology. He has been active on the lab's blog, having written weekly articles on the immunology of COVID-19.
Okay. Hi, everybody. So as Kristen mentioned, my name is Parker, and I'm going to be doing my best to, in the next few minutes, sort of summarize as much of the vaccine updates that have come out as possible. So first, I just wanted to start with a bit of overview about how vaccines actually induce immunity. So the first time that you're infected with a microbe or a pathogen, that pathogen is going to activate the immune response, and eventually you'll have production of T cells, antibodies, and eventually immunological memory that develop. But these things can take days to weeks to develop during the course of a normal infection. However, upon subsequent infection by the same or very, very similar pathogen, you will have a very rapid and robust induction of the adaptive immune response. And essentially, vaccines exploit this principle, and they mimic the initial infection to create memory, such that upon the initial actual infection, the immune system is already primed and can respond to the infection within a matter of hours or days. And in general, there are sort of two broad categories of vaccines. There are what are known as prophylactic vaccines, which are the vaccines that we're all familiar with for things like meningitis, hepatitis, etc. And the goal of these vaccines is really to induce immunological memory, again, so that when you're if you're actually infected with these pathogens, the immune system can ramp up very quickly. And the other broad category of vaccines are what are known as therapeutic vaccines. And these are the types of vaccines that are being developed for use currently to fight COVID-19. And the primary goal of these vaccines is to induce a potent immunological response rather than necessarily inducing memory. You may have some memory induction as a sort of byproduct, but at this point, the data isn't really out on that yet. In the case of any infection, the first step is going to be, or in the case of vaccination, the first step is going to be activation of the innate immune system. And so specifically, that's going to be your dendritic cells and your macrophages that take up the antigen and then present that to the naive adaptive immune cells, so the T cells and the B cells and the lymph nodes and the spleen, and eventually that'll lead to proliferation and differentiation into things like the cytotoxic T lymphocytes, the antibody secreting plasma cells, and culminating ultimately in the memory, immunological memory. So next, we're going to go through some of the major vaccine platforms that are in development for COVID-19, starting, of course, with the big one, the mRNA vaccines that are being championed by companies Moderna and Pfizer, Pfizer partnering with their German counterpart BioNTech. So in general, mRNA vaccines are a relatively new technology, and in fact, until November of this year, no therapeutic mRNA technology had ever been approved for use in humans. And so these vaccines are either viral or synthetic mRNA that encode specific antigenic components of the pathogen. The mRNA is injected, enters the host cell, and then it's translated by the host machinery to produce the viral antigen, which then elicits the immune response. One major downside of these vaccines is their inherent instability. mRNA is really unstable, and so that's where things like the lipid nanoparticle come into play, because they aid in stability and long-distance delivery of the mRNA. And this instability also means that these vaccines require extremely cold storage down to -80 degrees, which will undoubtedly hamper the efficiency of transportation and distribution of these vaccines. But one upside of these RNA vaccines is that they can be produced much more quickly than the traditional protein vaccines, and they induce stronger adaptive immune responses because the antigen doesn't have to be a near match of the viral peptide. It can be the physiologically correct version of the protein. So in the cases of the data on the slides here, unless it's specifically denoted phase 3, all of this is going to be from phase 1 or 2 trials. So both Moderna and Pfizer have seen success in their phase 1 trials in terms of limiting the number of serious adverse reactions. And they've also been able to quantitate neutralizing antibodies, Th1 responses in most of their patients and across all ages. And again, both these vaccines have shown at least 94% efficacy in preventing COVID-19 in phase 3 trials. So next up is the non-replicating viral vector. The biggest player here is the University of Oxford, partnered with AstraZeneca. They're developing their COVID-19 vaccine, which utilizes a chimpanzee adenovirus vector. And the other big one is CanSino Biological. So vector vaccines utilize recombination to force a viral protein to express a protein, they utilize recombination to force a viral particle to express a protein from another virus. And some of the most common vectors are adenovirus, measles, and the human parainfluenza virus. And essentially this is another method of inactivation, but it allows a much more targeted immune response because you can force expression of a single viral protein of interest. As these are non-replicating vaccines, the lack of replication means that these viruses are essentially avirulent. And so the induced immune response is much weaker. So these vaccines require boosters, follow-up boosters, in order to initiate development of a robust and sustained immune response. But like inactivated vaccines, because they're avirulent, they present a low risk of reversion and infection, and they can therefore be used in a wide population range. And so again, the data presented here for the University of Oxford and CanSino are from phase 1, phase 2 trials, in which none of these companies have really noted any serious adverse reactions. So now we come to what has been the big news recently, sort of the puzzling effects that have come, puzzling data that's come out of the AstraZeneca data. So the original press release published by AstraZeneca on the 23rd described their vaccine as being 70% effective at preventing COVID-19 on average, but it turns out that this 70% figure is more of an average of 2 different dosing regimens. So what happened was, in a small proportion of their sample, the first administered dose was only a half dose, and they chalked this up to what they're calling a serendipitous miscalculation. And so the individuals received a half dose, followed a month later by the full dose, which was within the parameters of the study. But what's interesting about it is the fact that the individuals who received the half dose followed by the full dose had a much higher efficacy of COVID-19 prevention than the individuals who received 2 full doses. And there's a lot of theories as to why this may be the case. It's been proposed that the lower dose of the vaccine is better at stimulating a T-cell response to support antibody production. Another theory is that because we produce an immune response to the chimpanzee adenovirus vector, the first full dose may have, in a sense, blunted the immune response to the antigen upon the subsequent booster shot. But again, these are just theories, and nobody really understands why this may be the case. On the bright side, AstraZeneca estimates that they will have approximately 200 million doses of their vaccine ready by the end of this year. And unlike the mRNA vaccines, these vaccines don't require extremely cold refrigeration. Okay, so next are the inactivated vaccines. These are being produced by Sinovac and Bharat. These contain viral particles that have been inactivated, most often via heat or chemical reagents. And these killed pathogens don't replicate in vivo, meaning that higher initial doses and subsequent booster doses are often necessary to induce an effective immune response. But again, the inactivation of these pathogens means that they're essentially avirulent. And so they can be used in a lot of the more susceptible patient populations, like the elderly, infants, and the immunocompromised. And in fact, some of the most prominent inactivated vaccines include the Salk poliovirus vaccine, hepatitis A, and the majority of influenza vaccines, seasonal influenza vaccines. And the last platform are these protein subunit vaccines that are being engineered by Novavax and Clover Biopharmaceuticals. These protein subunit vaccines deliver a very specific isolated peptide antigen to the immune system, and they're sort of the bare minimum in terms of necessary vaccine components. They contain only the parts that are essential for eliciting an immune response. So they don't contain live pathogen components, vectors, or anything like that. However, these vaccines require more precision to research and produce, because you have to determine not only which viral components will elicit the strongest immune response, but which viral components will elicit the desired immune response. And like inactivated and the non-replicating vaccines, these vaccines induce an immune response which is lower than for live or attenuated viral vaccines. And then lastly, I wanted to touch a bit on some of the data that's come out about side effects. So in neither Moderna's nor Pfizer's clinical trials have they reported any serious adverse reactions. However, minor side effects are inherent in any vaccine, and these are no exceptions. And in fact, both companies have reported these mild transient reactions, which for reference include things like sore arms, chills, malaise, fevers, etc. Both of these companies have reported transient reactions occurring at higher rates in their phase 1 and 2 trials than for the normal flu vaccines. And there's worry that this may dissuade people from coming back for the second dose or even for receiving the initial vaccination. And so I think that this high rate of reactions means that communication by the scientific and public health communities will be key for quelling some of the distrust and unwillingness to vaccinate that may present itself later in the year or in the beginning of next year. Thank you.
Thank you so much, Parker. Next, we have Cole Maguire, who will be talking about clinical trials. Cole is an undergraduate senior working under Dr. Esther Malamed while pursuing a degree in biochemistry. He has been managing Dr. Malamed's blog on COVID-19 and assisting on the lab's NIH COVID-19 funded research. He is also a rising MD PhD student.
Thank you, Kristen, for the introduction. And we're gonna dive right into it because there's a lot to discuss, luckily, on this topic. So obviously, there aren't many drugs out for COVID-19, but there are a lot in clinical trials, with over 4,000 clinical trials registered with the US government currently as of today. And across these trials, there are a wide range of therapies. And so we're gonna discuss some broad classes of them, not everyone, because we can't go over them, but just some of the most popular classes of drugs and why we are testing them for COVID-19. But before we get into that, I'm going to talk about two things. And the first is the clinical trial phases. So as Parker mentioned in the previous presentation, vaccines have 3 phases where drugs have 4 phases. And before that, there's preclinical work to show before we go into humans that there's evidence it might work. And then with each phase, you're increasing how many participants are involved and slightly decreasing the supervision as you increase that number. But that's how phases generally work. And you have to make it through all 4 phases and then apply for FDA approval. So that's very roughly how clinical trials work. And the other thing I wanted to touch very briefly on is COVID-19 response over time. So very early on, again, SARS-CoV-2 is the virus, COVID-19 is the disease. You have a response to the virus, but in some severe patients, it's been suggested that it's actually a response to over-inflammation. So you're entering this hyperinflammatory state. So when we talk about severe and mild COVID, it's somewhere along the spectrum where at some point it could just be hyperinflammation. And we're going to talk more about that as we go through this presentation. So the first class of therapies I'm going to touch on are called SARS-CoV-2 monoclonal antibody therapies. A monoclonal antibody, abbreviated MABs, are a mass-produced single antibody. So we've heard the word antibody flung around a lot today. They're Y-shaped molecules that your body normally produces in response to viruses. And so every time you have an infection, hopefully you're generating antibodies. They take about 2 weeks to kick in. And like Parker was showing, it takes time after that you get the vaccine for the antibodies to kick in. And that's what we're trying to get your body to have, because it helps fight SARS-CoV-2 by binding it when it's specific for SARS-CoV-2. So here, these are some antibodies that are binding the spike protein. And so these antibodies specifically target some part of the virus, and by binding it, it can prevent it from entering the cell, as well as mark it for the immune system saying, hey, that's not supposed to be here, attack that, degrade it, get rid of it. And so these monoclonal antibodies are single antibodies that we know bind SARS-CoV-2, and we can just give to patients, and then we can help their immune system mark these viruses for clearance. And so 2 of these monoclonal antibodies have emergency use authorization, which means temporarily until they finish their clinical trials, they have somewhat limited access in the healthcare setting, even though we don't know for certain how well they work. There's enough evidence to suggest for the FDA, you can go ahead and proceed with treating some patients with this because of the circumstances are very dire right now. So these 2 therapies are casirivimab and imdevimab, which is actually 2 monoclonal antibodies that bind to different parts of SARS-CoV-2, and they're mixed together, and this is called RAIN-CoV-2. This was made very popular when the president a few weeks ago received this therapy and made the news a lot. And the second one is bamlanivimab. So both of these do have EUA approval. However, they are only approved for mild patients. So again, we think back to that graph I showed, when the viral titer is very high. So when you have a lot of virus in early stages, that's when these therapies are looking to be most effective, where once you've cleared the virus and you have this hyperinflammation, they wouldn't be as effective because the virus isn't really there anymore necessarily. And so it's very useful early on and in mild patients. There's been no efficacy found in the large trials in these severe patients, again, suggesting, this is for early for the most part and mild, and that's where it's going to help and make the most significance. To contrast monoclonal antibody therapy, we also have convalescent plasma, which is also getting a lot of attention in the news. It's also received emergency use authorization from the FDA, and it transfers plasma from recovered 19 patients into hospitalized COVID-19 patients. And this plasma contains those patients' developed antibodies. So here we're getting the antibodies from a different source, those who are already infected. And so there has been some debate over its efficacy due to conflicting study findings. Again, those conflicting findings might come from what we now know to be the timing of this drug is really important to how successful it is. And then briefly, I want to touch base on why are we trying to ultimately get to monoclonal antibodies and away from convalescent plasma. Convalescent plasma is very expensive, and there's a limit on production because we're collecting it from people who have recovered. And you can only collect so much from those participants. And even furthermore, in the plasma, it's not just those antibodies. It's all the antibodies they produce. And we have so many antibodies in our blood, as well as other proteins. So it's not just, it's not a pure drug. Where monoclonal antibodies, one, they're mass produced, and so we can produce a lot, and they're cheaper. And it's specific to SARS-CoV-2. So we know exactly what we're giving the patient. Whereas convalescent plasma, we don't necessarily know. We know that the SARS-CoV-2 antibody is in there, but we don't know what else is necessarily. So that's why we're ultimately trying to get to monoclonal antibodies and why so many are in development. The next class of therapies is antivirals. So antivirals attempt to slow or stop viral replication. So again, this would be a therapy that's really useful early on in disease, we think, because if you're going to prevent the virus from replicating early on and give your immune system more time to fight it before it can get to really high amounts in your body. And so often it targets viral-related proteins such as their transcription, their packing enzymes, their replication proteins. And remdesivir is the one that's garnered the most attention, being the first FDA-approved therapy for COVID-19. So non-emergency use authorization actually approved for COVID-19, and has become the standard of care in the US, often using being the placebo group in many of the other trials for all these other drugs, comparing to remdesivir now that we know it works. Another antiviral was a leponavir-ritonavir combo, which has been popularized for HIV, but it was not found to be effective in COVID-19. But you might have heard this really early on in the pandemic. This is one that people were testing out a lot. And then Pfizer is also testing another broad spectrum antiviral that shows really good results against all types of coronaviruses. Although this is early on in development, so it may be a while before this one gets here, although it does look really promising. The next class of drugs is immunomodulatory therapies, and this is a very broad class. And these are drugs that just target a specific branch or pathway of the immune system. So they can augment or suppress part of the immune system. And so they have different mechanisms of action. So some examples are interferons, JAK inhibitors, CVC, or Renica. Interferons is probably the one that's got a lot of attention early on. And these are typically considered antivirals. So they just help your immune system and tell it, hey, there's a virus present, prepare viral response mechanisms. JAK inhibitors, CVC, or Renica are all really good at reducing inflammation and reducing immune activation. So they might be good in later stages when we have this hyperinflammation. And so that's what they're being tested for. So speaking of this hyperinflammation, a lot of these remaining classes of drugs are going to talk about that. The next one being corticosteroids, which are generally anti-inflammatory. And dexamethasone is the one that specifically has gotten a lot of attention because of the recovery trial out of the UK demonstrated a 10-day treatment of this drug reduced deaths by 1/3 in ventilated patients. And so this is really interesting because contrasting this with the antibody therapies we talked about earlier, this therapy demonstrated efficacy in the severe patients and not in the mild. So there was no benefit in the mild patients in this study, but there were in the more severe patients. And as you increase severity, the more useful this drug became. Again, this kind of helped confirm and support the hypothesis that later on in these severe patients, it may just be hyperinflammation that's giving them a lot of symptoms and causing a lot of damage to the body, is that there's just too much inflammation. So if we can give anti-inflammatory drugs at those stages, then we might be able to help those patients. Also, another class of drugs on this anti-inflammatory front is the cytokine monoclonal antibody therapies. So we talked about monoclonal antibodies earlier. And again, they're also being used, but this time they're against different cytokines, which are small secreted molecules from your cells. And they're kind of like text messages between the cells. They help communicate across cells. And so like some of them could be inflammatory. Some are saying like, hey, we're going to be anti-inflammatory. Hey, activate this, turn that off. So they're really useful communication networks between the cells. And we've seen an increase in these inflammatory cytokines in these patients in what's called the COVID-19 cytokine storm. And to target this storm, many antibodies against very specific cytokines have entered clinical trials to see, hey, if we like try to stop one communicator in this network, could we potentially reduce inflammation? So some of these ones that are being tested are IL-6, GM-CSF, and TNF, all of which are cytokines, very technical terms there. But no trial has found really good efficacy in phase 3 or later. Usually they show slight efficacy early on, but once they get to the larger trials, we don't end up seeing significant results, although there are many still in clinical trials. And then the final class of therapies I'm going to talk about are antithrombotics. So many severe COVID-19 patients develop what's called COVID-19 associated coagulopathy, or an overabundance of clotting. And so in their blood, they just have increased clotting factors. And so it's causing strokes sometimes, and it's causing all sorts of problems that you might have heard about, such as the microclots across bodies and cadavers. And so luckily, the US did start a trial for this, which is really great to see, called the Activa-4 trial, which is studying blood thinners such as aspirin, heparin. And they're looking at which of these, as well as dosing, would be effective in specifically COVID-19 patients with this CAC, or COVID-19 associated coagulopathy. So in summary, there are many challenges that clinical trials face in the coming months, especially as the pandemic continues to surge and expand. But there are many great candidates in the works for these clinical trials. And so I'm sure we're going to see some great drugs come out of it. However, we should be cautious not to rush the trials, because we've seen what happens when that occurs. That's when errors happen. These trials are happening years faster than they normally would, but we still have to conduct strong science, because at the end of the day, that's what clinical trials are. They're science, and science takes time. But they will come eventually, and there's so many great drugs in the work, and it's going to be exciting to see what the next year holds.
Thank you, Cole, for that presentation. And for our final presentation, we have Emily Bateman. She is originally from Denver, Colorado, and is currently a first-year medical student at the Paulo Foster School of Medicine in El Paso. She is studying medicine and public health.
Thank you so much, Kristen. All right, let's see if I can get my computer working for us today. Okay, so I can get rid of that for us too. So I will be talking about our minds during this pandemic of ours, and this presentation was put together by my lovely colleagues, as well as Dr. Longhurst and Dr. Jansen. So just a quick disclaimer, again, we are not giving any medical advice. Please go see an actual professional if that is what you are needing. And we don't have any financial obligations to report either. So before we actually get started in this, one of my classmates has been studying this presentation, how to make it better. So if you wouldn't mind just filling out that poll, we won't judge you. There's no wrong answers. If you could please just help us out, it just helps us make this presentation better for the future. All right, and I'll just give it a little bit more time. No worries if you're still working on it, but I don't want to keep you guys too much longer since I know you guys are in the midst of your evening. So, all right. So what's going on? We are going through a period of widespread disease. Most of us haven't experienced this in our lifetimes, and our daily lives might have been turned upside down. And for some of us, maybe they don't look too much different. Some of us might be feeling really down or nervous or just plain unsure about how we're supposed to be feeling. So what's changed? As we go through this presentation, there's these little boxes in the top right. Just take a moment to kind of think about how they apply to you, and ask yourself those questions for reflection, because it's different for everyone. But as a general rule, what's changed for a lot of people, it's how much time we're interacting with family or friends and how we're doing that. Our school routine might be different, how we're taught might be different, same with our work routine, our plans for the year, and especially going into the holiday season, finances and celebrations have been looking a lot different as well. So what do we worry about? Maybe for some of us, it's getting the virus, or family getting the virus, friends getting the virus and getting sick. The future, I know that it looks really unsure in some places. Safety in schools, what school's going to look like, what workplaces are looking like. Again, finances are a really big stressor, and losing someone to this virus as well. So how do we feel? The pandemic acts as a stressor. So that means it affects both our mental and our physical health. So people who are working might feel afraid or burnt out, or just tired. Some of us with mental conditions might feel our anxiety or depression worsening. And sick people, those of us who might have gotten sick from this, might feel guilty or self-blaming, or afraid as well. These are just some more adjectives to kind of put into words what you might be feeling. So relaxed, angry, excited, abandoned. There's so many things that you might be feeling. And why are we feeling some of these things? Some of us are experiencing the process of coping with the loss of someone, or maybe the loss of a job. Again, those stressors from the previous slide come into play. So we might feel like we don't have the energy to do anything. Maybe we're having difficulty sleeping, or maybe we're sleeping too much. Some of us might feel like we can't go on, or we're feeling really sad or worthless or guilty. Some of us might stop eating, or again, eat too much. Maybe the things that we liked to do before aren't interesting anymore, and we haven't been able to concentrate on things. And some might feel like we want to hurt ourselves. And if you do feel like hurting yourself, please call 911 if it's an emergency. Otherwise, these other numbers on here are some really amazing resources. So please take a minute as I'm talking to put these in your phone. You never know when it might help you or a friend or a family member or a coworker. So this, if you're in El Paso, this is the crisis hotline for El Paso. This is the crisis hotline for Austin. And then these are two national hotlines that are really, really great resources. So I'll just hang out here for a second. If you can write them down or put them in your phone, again, you never know when you might need them. All right. So if there is anything that you take away from my talk tonight, please know that you're not alone. There are people that want to help, and they want to help you. So if you feel comfortable, talk to the people close to you. They do really want to help, I promise. And if you don't feel comfortable with that, that's okay too. Please talk to a doctor or a mental health professional or a school counselor if you have one. And again, you can also talk to someone who's on those crisis lines. They are a really, really great resource for when you are feeling down. And another thing that I do want to talk about as well is some of our unhealthy outlets. So some of those emotions that we were talking about before, sometimes they get channeled into really, really unhealthy habits. So maybe that's drinking too much alcohol or using drugs, smoking, or hurting others. It might feel like they're helpful at the time, but these are false outlets, and ultimately they do end up hurting us more. So some people are hit, slapped, kicked, or abused in other ways by family members or strangers. Please know that this is not okay and you can get help. Again, if you are in an emergency, please call 911. And if you're not in immediate danger, the Department of Family and Protective Services, as well as the National Domestic Violence Hotline, can really help out and provide you with the information that you need to get yourself into a safer situation. So we talked about why we're feeling some of the things that we do and what we're feeling. So how do we help ourselves? I think the biggest thing is just being aware of what you're feeling. That can be really difficult at times. So if you can take a moment and reflect and figure out what you're feeling, then sometimes it makes figuring out how to get yourself to stop feeling that way feel a little bit more manageable. So again, ask for help if the pandemic is affecting your life too much, or if you're just feeling burdened or downed, or worried even. Know that feeling this stress and fear is normal, especially as we go back to school or work, and especially heading into the holiday season as well. Thankfully, with modern technology, keeping in touch with friends and family is definitely a little bit easier. So send a text or reach out on social media or video calls. That's what my family's been using, and it's been extremely helpful during this time. Another great thing to keep in mind is just listening to your body. Keep a schedule for your day if you can. Try and eat your fruits and vegetables and exercise every day, and follow those CDC recommendations for wearing masks and avoiding to touching your hands, your face and nose, as my colleagues have said before me. Another cool thing that I think often goes overlooked is your sleep hygiene as well. So instead of mindlessly scrolling through Instagram at the end of your day, try and keep your phone off for the last half hour before you head to bed, and don't head to bed with the TV on. So there's some really amazing resources for sleep hygiene practices as well if you're interested in that. And keep a positive attitude. And I know that for some of us that might sound really difficult to do, but the pandemic will end. We don't know when, but it will eventually end. So just have empathy for yourself and your journey going through this, as well as the people around you. So as we've done this talk, a couple people have asked, how do we help children? And the biggest thing is just being patient, kind of the same thing as you would do with any adults. where a lot of us are scared. So talk openly about feelings and concerns, and don't try and hide everything away, and just listen to what they're afraid of as well. Some of our kiddos are doing online school, and I know that that's a big shift, especially working from home for some of us. So just be patient with the curriculum. So these two websites, the first one is a Johns Hopkins website as well for how to help your child stay focused. And then this last website is actually from our EP Heat website, and there's a little pamphlet infographic about coronavirus for both adults and children. So how do we help others too? We kind of talked about how to help kids and ourselves, but how do we help others? Kind of what you would want other people to do with you, right? The golden rule. So check in on them often, especially if they're older, especially if they're sick, especially if they're feeling lonely or down. Keep an eye on each other as well. So whether that's a family member or a friend or your kid or someone else's kid or a teacher, just keep an eye on each other. We're all in this together, and it's a group effort. We're all feeling the stress and varied levels of emotions that go with it. And so again, just be patient and have empathy for ourselves and for everyone else around us. And that is kind of the conclusion for mine. So if you wouldn't mind, again, just filling out that post-talk poll, that helps me a ton. And as you're doing that, I'm just going to go into this next slide. Usually with our longer sessions, we could go through a mindfulness exercise and a deep breathing activity. However, since we are short on time, I don't want to take up too much more of your evening by rushing through a breathing exercise, as that kind of does the opposite as what we want. So check out these resources. They're really great for just kind of getting centered again, and maybe even feeling a little bit less stressed or whatever other emotion that we might be feeling during this pandemic. Thank you so much, and I hope you have a great rest of your evening.
Thank you so much, Emily, for that presentation, and hopefully she'll be able to drop those links into the chat for all of you. This concludes our presentations and begins our Q&A session. And so we have one question for whoever would like to address it so far, but are the rapid point of care and saliva test PCR tests? So I will, someone from our panel to speak. Nive, it's hard to hear you, or maybe you're muted.
I'm sorry, is that better?
Yes.
Okay, awesome. So, so the rapid point of care test, those, there are a few different types out right now. Some of them are PCR tests, and then some of them are antigen tests, which means that they are looking for proteins on the virus particles. There's also, and then the saliva tests, these are PCR testing. So it essentially works the same exact way as like the PCR testing that we discussed in the presentation. The only reason that the results come out faster is that there are a few steps that kind of get expedited. So like the saliva testing that doesn't require extracting like the nucleic acid before testing, and then there's just some flexibility with the different reagents that are used and equipment, which really expedites the process. I hope that answers the question.
Yes, thank you. The next question we have for our panelists is, if you receive the vaccine, how is your immune response tested?
So in general, in most of the studies, what they're looking at is the antibody titer, and specifically the neutralizing antibody titer, because it's great if you have antibodies, but it's not much use if they're not preventing infection. And so that's what the titer of neutralizing antibodies represents. And so in the majority of their phase 1, phase 2 trials, excuse me, not the phase 1 and phase 2, but in the phase 3 trials where they're looking at efficacy, that's what they're measuring, is both the titer of neutralizing antibodies as well as the duration of neutralizing antibodies. So in the case of the mRNA vaccines from Moderna and Pfizer, it's looking like, in general, at least from specifically, I guess, Moderna, the neutralizing antibodies they're induced roughly 10 days after the second full dose of the vaccine, and then they're lasting in some cases up to day 119 for a specific figure. So they're lasting roughly 3 months. And in a lot of the data that's come out that's been published in the New England Journal of Medicine, that's what they're essentially denoting. And then they also make a note that they're still looking into the induction of immune memory. So that'll be looking at the memory B, memory T cells, things like that, which hasn't really been carried out yet.
Thank you, Parker. Our next question for the panelists is, why is there so much worry about reinfection? If having COVID does not protect you from a future infection is true, then why should a vaccine work?
I think a lot of it has to do with the rate at which the virus mutates. So in the cases of reinfection that we've seen, I believe in China and also in the United States maybe, but correct me if I'm wrong, those were they weren't reinfected with the exact same strain of the virus, or more, it's technically an isolate. So these viruses don't have, a strain denotes when viruses have different biological properties, whereas an isolate is just a difference of maybe 1 or 2 nucleotides in the genetic code. And so in the cases of reinfection, a lot of those were with different isolates of the virus. So it's the case that, it may be the case that while our specific immune response, and I'm sort of just spitballing here, but if our immune response, can't protect us from strains that differ in terms of the genetic code, it may be the case that perhaps these these vaccines may do a better job of protecting against the virus in general, if that makes any sense. There have been instances of individuals in these trials who are asymptomatic, and they have been found to have neutralizing antibodies against some of the other human coronaviruses that cause the common cold. So that's, reason for optimism. So it's sort of, it varies, I think, from person to person in terms of history of exposure and that sort of thing. Hopefully that helps.
Yes, thank you, Parker. And just to emphasize a comment that was put in the chat, that the vaccine can activate the immune response in a different way than the virus itself. So sometimes it can be more effective than the response than the actual virus. So thank you for that comment. All right, I will allow a couple of minutes for those of you to think of some questions for our panelists. In the meantime, I'll go ahead and share my screen to show some opportunities to learn more about EP heat. So this is our homepage. If you go to the ttuhsc.edu homepage, on our very front page, you'll actually see some information regarding EP heat. Right here that you can click on and learn more. So if you click here, it'll take you down to an article about how we got started and how you can get more involved. And let's see. I will also try to figure out how to show you the Facebook page that we have in addition to Dr. Melamad's blog. But if you go to type this in, you can also subscribe for weekly scientific updates as well from the team at Dell Medical School and UT Austin. And then I will pull up the link for the Facebook page and the other in the meantime. Okay. Okay, so we have another question. When will the city government reveal where the hotspots are?
I believe in El Paso, we have the El Paso Strong website where we can see cases by the zip code, as mentioned by Dr. Walker. And from our UT side, do you all know of any citywide websites that show you where the hotspots are?
Yes, the city of Austin has a data portal showing it by zip code as well. And I can send a link in the chat.
I believe the Johns Hopkins website also has information on that, so I will also post the link for that. They have a lot of data, and so it is pretty variable in terms of how much they go down in terms of zip codes, but I'm pretty sure they also offer that.
Yes, and I'm also posting the links to the YouTube channel where you can subscribe, and also a Facebook page where you can subscribe to EP Heat as well. Okay.
I guess I'll ask a question. By the way, I wanted to say great job to all of our panelists tonight. It was a very educational discussion, very educational talks by our panelists. So thank you very much to all of our students from UT Austin, from UT El Paso, for presenting tonight. And I have a question for all of you guys on the panel. I'd love to hear your thoughts. What do you think is going to be the efficacy of vaccinating individuals who have had COVID previously?
So I can jump in a little bit. So it definitely depends. Like there's some evidence to suggest that months out from the initial infection with COVID-19, their antibody titers can actually decrease. So potentially long-term, it could help. I think there hasn't really been enough data yet. The FDA did say they were going to require it, but I think they've passed that, that they specifically tested in previously COVID-19 confirmed positive participants. But I haven't seen the data for that, and I think they are kind of looking to do that down the line, but they're really trying to get the vaccine out there. I do think it's a really interesting question, but ultimately, I think it will be important potentially to revaccinate. I think the coronavirus long-term is also going to kind of be like the flu shot, right? Now we try to get that every year. It is a widespread virus and will continue to mutate similarly. So it may be something that we have to continue to get vaccines for. And just like the flu, even if you've had it, you can still get vaccinated for it after, and it can still be beneficial. Because like was mentioned earlier in the comments in the chat, the vaccine is really like the perfect scenario. It's trying to design the perfect scenario for the optimal antibody response and the optimal immune response. And infection doesn't always necessarily look like that, which is why sometimes you have reinfection at low rate. Maybe they didn't generate a good immune response around the first time. And so even with small mutations, it predisposed them, and it was enough for them to have another infection. Maybe the first infection was really weak, so they have a weak immune response. So I do think it's going to be important to vaccinate, because vaccination is a very controlled immune response in which we're trying to create the perfect scenario to help it generate antibodies.
Yeah, going off of what Cole and along the lines of what Dr. Walker said, it may be the case that individuals who were infected developed an immune response to a different epitope or a different antigen of the actual viral particle itself, different from what a vaccine may induce immunity to. And so I think that in that sense, it would be important and also efficacious to vaccinate individuals who had already been infected. And in the New England Journal of Medicine, there have been more reports on these Moderna and Pfizer vaccines that have just come out in the last week or so. And again, they don't really describe any data on immunological memory. And so it'll be interesting to see whether that's a significant portion or significant factor in, lasting immunity to the virus, and whether vaccination will be essential in those who have already been infected or been vaccinated multiple times, perhaps.
Can the panelists please talk about the importance of, one, getting the vaccination, and two, there's a 2-dose schedule for vaccination. So what is the importance of the second dose?
So based off what I've seen, it looks like those who received the efficacy for individuals in terms of preventing COVID-19, for those who received only the first dose was roughly 65%. So in terms of maximizing the efficacy of the vaccine, it's really important to get the full regimen, the 2-dose regimen. And again, that has to do, I imagine, with the fact that because these vaccines are essentially inactivated or attenuated, you're not going to be producing an incredibly robust immune response on the first dose. And so that's why it's important to get the full regimen, the full dosing regimen.
Thank you for that. So the first one kind of primes the immune system. The second one serves as a booster to get that efficacious immune response. I want to just thank the panelists. Thank you to our students. Thank you to Dr. Malamed for this great collaboration within Texas Tech and with UT Austin students. Our students did an absolute fantastic job on their presentations, and I really want to thank them for being available to be our panelists for today. And I'm hoping this is just the start of our collaboration. And I want to thank Ms. Kristen for being our student moderator today and setting this up. She was kind of the glue to bringing Dr. Malamed and I together to host this joint panel. So thank you, Kristen, for bringing us together for this opportunity. And with that, I'll go ahead and pass the virtual mic to Kristen to close us off.
Yes, I just want to echo what's been said. Thank you so much to our panelists. It's been a pleasure to work with all of you. And I also look forward to collaboration in the future. I posted the links to the YouTube and Facebook page if you would like to learn more. And with that, we conclude today's presentation. So thank you all so much for coming, and we hope you learned a lot.